In this video, we're going to look at rotational kinematics. Some of this stuff is related to what we did in circular motion. So some of the ideas will be familiar, but we need to kind of make those connections. And then we're going to talk about rotational inertia. Yeah. So review / talk about rotational kinematics. We kind of brushed over this in our circular motion unit, so it'll be less review than it might have been. And then we'll define and calculate rotational inertia at the end. The big thing I wanted to kind of look at was, see if I can move my face out of the way. There we go. The variables that we have to deal with when we're talking about rotation. Now, in translational motion, we had time, position, displacement, linear velocity, acceleration. We know all about those. Time is the same thing, but everything else is slightly different when we talk about rotation. In terms of position, we're not talking about physically moving it through space. We're talking about rotating it some angle. And this is usually given the symbol theta. It is measured in radians. Then you have angular displacement, right? How much did you move from a starting point? Same idea. Angular velocity, how many radians per second? That's an omega, a lowercase omega. And then angular acceleration, that's an alpha, radians per second squared. We also have some equations, and you could go through a whole derivation of these if you want. It's the same as the derivation for them in translational quantities, but you notice that we have the same, essentially, 5 equations. I guess, sorry, 4 up here. You can also do one where the third equation is solved for the initial position, both angular and translational. That would be the 5th. But these are the rotational equations. And, you know, some of these occur on, just like some of them occur on your equation sheet for the AP, some of the rotational ones do as well. So what do we do with this? Well, when we're talking rotational kinematics, you think about a rotating wheel. This is always a good way to think about it. It has some displacement angularly, it has some angular velocity and some angular acceleration, or at least it could, given certain circumstances. But any point on the wheel, literally any point, not just on the outside, but the outside points are the easiest ones to talk about at first, also has some displacement, right? It's moving through space if you were to track that point. And that's essentially circular motion, what we've already talked about. It has a change in basically arc length, right? Position along that arc. It has a tangential velocity. It could have a tangential acceleration. It could be getting faster or slower. It certainly has a centripetal acceleration because it's being pulled in a circle. And then there's a net acceleration combination of those, right? So how are these things related? That ends up being important because it can be pretty easy for us to measure how many times we go around a circle. So 2 pi radians, and then count how many of those we had, use a stopwatch to get a timer, and that'll tell you about angular speed, angular displacement. If we know the radius, though, we could talk about how far or how fast a point on the edge has traveled. And so this is the general idea, right? If you're talking about a point on the edge of the circle, then what is the rotational variable to the translational variable? Well, the arc length is related to the delta theta and so on. So what do we get? Theta is equal to S over R, arc length over radius, which means the linear displacement, delta S, is equal to the change in theta, the angular displacement times R. Right? So linear displacement is angular displacement times R. Right? And for a point on the circle, that's just the radius of the circle. We can do that for velocity. Well, we know that velocity is change in position over time. Angular velocity is change in position, angular position over time, right? So if we take the time derivative of both sides of this equation, or basically turn those into, instead of delta s's, into ds dt's, we get v, linear velocity, is equal to angular velocity times r. We could do that one more time. What is the linear acceleration or the tangential acceleration, right? dv dt, d omega dt. D omega dt is alpha. dv dt is tangential acceleration. And I put that whole subscript there because this is not centripetal acceleration. That has a whole different definition, which we'll get to. Okay, but those are the first 3. Linear acceleration is angular acceleration times delta r, or times r, the radius. What about centripetal? Well, centripetal acceleration is defined as v squared over r. And we already know that v squared, that v is omega times r. So if we plug that in, we get omega squared over r, or omega squared r. This could also be called the radial component of acceleration, right? Radial in, tangent to the circle, as we sometimes see there. So the summary, we have displacement. Linear displacement is equal to angular displacement times r, linear velocity omega r, tangential acceleration alpha r, and centripetal acceleration omega squared r. Right? What are the units? Radians times meters is going to be meters, because radians is essentially unitless. Radians per second times meters, radians per second squared times meters, and so on. Okay. So let's look at some examples here. How do we think about this? An astronaut in a 10-meter radius centrifuge. This is one of these devices designed to test how you react to big, huge g-forces, centrifugal forces, but really, really big accelerations, much greater than the acceleration due to gravity, right? And it has, kind of the ability to speed, move through space like this. The equation for the motion is 0.3 t squared. At 5 seconds, what is the delta omega from the starting point? The delta theta, the angular displacement, the angular velocity, the angular acceleration, the linear displacement, the linear velocity, the tangential acceleration, the centripetal acceleration, and the net, right? A lot of things to calculate. But we have all the relationships, right? We start with delta theta equals 0.3 t squared. We plug in the time, and we find out that it travels through 7.5 radians. We take the time derivative of that equation to get 0.6 t. We plug in 5 seconds, and we get 3 radians per second. We take the second time derivative to get alpha, which is just a constant 0.6 radians per second. Right? So we have a constant angular acceleration, which means all of our kinematics relationships for angular kinematics will apply, which is great. If we want to convert to displacement along the arc, so linear displacement, we get about 75 meters. We can do that for linear velocity, 30 meters per second, tangent to the circle at that point in time, right? Then we can get on to acceleration. That's alpha times r. So we get 6 meters per second squared tangentially. That's how fast it's speeding up in a line. Centripetal acceleration or radial acceleration is 90 meters per second squared, right? We can put those together. Centripetal is into the circle. Tangent is tangent to the circle. They're perpendicular to each other, so we can just use the Pythagorean theorem to get 90.2 meters per second squared, kind of angled that way. So kind of to follow up here, if you're halfway along the arm of the centrifuge, right, where there's some components, I don't know, what's going on there, but, somewhere right along here where the words are, which of these values change? Well, all of the translational values depend on r, but all of the angular values are true for every part of that. So that's the key, that the angular stuff is the same for everything, which is why it's an interesting set of variables to look at. And the translational variables, they all, and their values, all change depending on where you are along the rotating object. So can we use kinematics equations? In this case, we could, because alpha was constant. I alluded to that earlier. But if it isn't, then you can't use those equations. So what's the big picture here? Well, Newton's first law, right, in translational relationships, we already talked about this with statics and static equilibrium. Net force is 0, net torque is 0. So it follows then that the net force equals ma for translational motion would have a similar relationship where net torque equals something. So we haven't really talked about these quantities, and we will, but mass, which is just inertia, is replaced with rotational inertia, which gets a capital I, and acceleration, linear acceleration, is replaced with alpha for angular acceleration. So what are our key variables now? Force and mass, the inertia, are what matters to find acceleration in translational motion. And now it's torque, which is related to force, right, that can cause rotations, and I, or angular inertia, or rotational inertia, also known as moment of inertia. So rotational inertia I, how do we think about it? Well, there's the concept of it, and then we need to define it and do some examples. We'll also come up with a little bit of a derivation. So conceptually, the idea is that rotational inertia is the tendency of an object to resist changes in its rotational motion. So if you think about translational motion, if you double the mass, you need twice the force to get the same acceleration. So the same idea applies here. If you double the moment of inertia, you would need twice the torque to get the same angular acceleration. So imagine this. If you had a ruler and you were to sort of attach a mass to it, if the mass was low down near your hand, and you're trying to keep this balanced, or you put the mass at the top and tried to balance it, which one is easier? Who wins this, test of balancing? Well, probably, right? The person with object A wins because the pivot point is right at your hand and the mass is closer to it, so it's not going to move around as dramatic of a way. Whereas in B, if it goes off balance a little bit, it's going to fall, right? And so what we say here is that the one that is sort of harder to control is the one with the larger moment of inertia. So you can try this. If you grab a broom or something like that that has a long handle and something more massive at one end, hold it at the end of the handle and sort of swing it around, twist it. Then hold it near the mass and twist it. And what will you notice? You can pause the video and go try it. But what hopefully you notice is that the rotational inertia depends on mass and where it is, right? The moment of inertia increases as you move the mass further from your hand. So here's an example. If you were to have two identical masses on a rigid rod, and you were to put them close to the middle and you were to twist them, that would be very easy. But if you were to put them out further and twist them, that would be hard, right? And that is because the moment of inertia, the distance depends on the distance from the center. Small moment of inertia where all the mass is near the pivot point, large moment of inertia where it's far away. Now this bears pausing for a moment. Because if I were to grab either of these from one end, I would get a different result, right? Right now, and try to spin them. If the pivot point is in the middle, they have a particular moment of inertia. If the pivot point is somewhere else, they have a different one. So because of that, although the mass of both of these is the same, no matter how you hold it, the moment of inertia depends not just on where the mass is along the rod, but also what you call the pivot point. So how do we define moment of inertia? Well, if you think of a bunch of individual little objects arranged along a rod, what you end up having is a weighted kind of position average that depends on where you are. And so this formula might look a little bit like center of mass, except for the 1 over m. But its units are kilograms meters squared. The big difference is that it depends on position squared, not just on position. We're going to also look at the integral form of this with our next look once we've kind of figured out how to do this for individual objects. But let's look at an example of how this works, right? So if you take two objects that are connected by maybe a rigid rod and say, what is the moment of inertia? Well, we need to pick about what point. So 3m and m are attached to this thing. And then we have a pivot where it balances. So that's the center of mass, right? And so we can find the center of mass. Relatively straightforward. Now we have a second question. What is the moment of inertia about that pivot point, right? Well, if we have the center of mass formula, it says you take the mass multiplied by its position along the line squared, and so on, right? One of them, or not its position, excuse me, its distance from the pivot point. And that's the difference too. In center of mass, the calculation cared only about, right, where they were relative to any arbitrary point. But here, we need to be thinking about distance from the pivot point. So even though this 20 centimeters is to the left of the pivot and the remaining 60 is to the right, both of them, right, are measured positive because they are distances away from the pivot point. It wouldn't matter if you wrote negative here because they're squared, but that is how we define it, right? So if we move the axis, which is the highest moment of inertia? If we put the axis at A, at B, or at the center of mass? Well, if we put it at A, right, then A does not provide any rotational inertia, so it's only B, which has the small mass. If you do it at B, the big mass is pretty far away, and you get that. And then it is lowest, you will find, when we are at the center of mass. And this is why, if you just fling an object that is able to rotate out into space, it will rotate around its center of mass, because that's the lowest moment of inertia occurs then. And of course, objects moving don't want to change their motion, right? The amount of force is going to just cause it to do its bare minimum in that case. We could do this in 2 dimensions, right? If we needed to. The axis is going in and out of the screen. And so we can say, what is the moment of inertia in about the x-axis, the y-axis, the z-axis? If we wanted to, along the x-axis, it really just depends on how far up you are, right? So this is 9 kilogram meters squared because it's a 1 kilogram object, 3 meters up. Excuse me, my phone is ringing. And so that's what we're looking at there. Then if you do it about the y-axis, you get a slightly different result, right? Because it's a different distance from the y-axis. It's 4 units or 4 meters, so that's 16 kilograms meters per second. And then from the z-axis, we have to be a little bit more careful. It's a diagonal distance. This is a 3, 4, 5 right triangle, so it's a distance 5 from the z-axis, and you get 25 kilogram meters per second. So depending on how you rotated this, you would have a different moment of inertia. When it comes to an object that is not a point particle, but we put the axis of rotation around the middle and all of the mass is out at the edge, this is kind of like your basic wheel or hoop. In this case, well, the moment of inertia of the hoop is every bit of mass the same distance r away. So this one is actually pretty simple. It's just m times r squared. We'll look at what happens when the mass is distributed in different ways next time. So how do we derive this? Well, think about kinetic energy. Does a person rotating on a stool have kinetic energy? Yes and no, right? The velocity of the center of mass is 0, so they're not going to have any kinetic energy in a translational sense. But every bit of this person's mass is moving, so there is kinetic energy, which we call rotational kinetic energy. And it comes from this definition, right? This idea that rotational kinetic energy is 1/2 mv squared for every individual little particle put together. And so for a system of particles, if you kind of let them rotate at some angular velocity, right, we can say, well, v, the linear velocity of each of them, can be calculated. Mass 1 times omega r1 squared, mass 2, omega, and so on. And if you kind of expand that out, they all have the same angular velocity, right? So we can pull that out. And then we have 1/2, a bunch of stuff, times omega squared. Well, that looks a lot like 1/2 of the moment of inertia times omega squared, because each of these are the moment of inertia or rotational inertia for the individual particle. So we come up with this last line, which is that 1/2 of I omega squared is the rotational kinetic energy of the system. All right, so that's the end of that. I know there was a lot in that video, kind of 2 pieces, the kinematics recap, and then some stuff about moment of inertia, and we'll keep looking at that as we go.